If your loss explodes or never moves, it's usually the learning rate. We'll run a tiny experiment that shows 3 regimes: too small, good convergence, and divergence, so you can recognize the pattern instantly. You have felt this pain. You train a model and the loss sits flat, or it shoots to the moon. That single knob, named learning rate, often decides the fate. After this video, you will spot which regime you are in and pick a simple fix. You will also learn a tiny automatic trick to test a rate before committing many hours of training. I'm Professor Pi, teaching AI foundations from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. Learning rate and convergence matter because gradient descent is the backbone of most training loops. In practice, it solves optimization problems like fitting a regression or tuning weights for a small network. People reach for it because it is simple and effective. But the downside is sensitivity. A wrong rate wastes compute or wrecks your model. Compared to adaptive optimizers, plain gradient descent gives clearer intuition, which is what we want for this experiment. At a high level, we will use a tiny convex loss, think of a smooth bowl, and run short training runs with different rates. The goal is visual and diagnostic. You will see a slow creep, a clean fall into the minimum, and a blow-up. Strengths: it teaches you regime identification and quick fixes. Weaknesses: this toy is small, so real networks add noise and curvature, but the basic patterns still hold. We will build 5 tiny scripts. First, we define the loss and check the gradient. Then we run many tiny steps to show slow convergence. Next, we sweep rates and pick the best. After that, we show a too large rate that diverges and then rescue it with decay. Finally, we try a one-step look-ahead to pick a safe rate and train. This keeps everything focused and repeatable before the code drops. This snippet defines a tiny convex loss and shows its gradient at start. This example sets up a simple optimization landscape, the kind of smooth bowl where a single global minimum exists. It computes the scalar loss as a function of a parameter, and then computes its gradient at the initial parameter. The key lines create the loss function and then print or return the gradient value, so you can see direction and magnitude. This shows whether the initial step should move left or right, and roughly how large a change would be if you took a unit step. In real work, this maps to a single weight or a low-dimensional prototype used to debug larger models. Now we will run many tiny steps to see what happens when the rate is small. This snippet runs many tiny steps to reveal slow convergence. This example repeatedly applies gradient descent with a deliberately small learning rate for many iterations. The loop shows loss values at intervals so you can watch the curve slowly descend. Key parameters are the number of iterations and the small rate itself, which you will see causes the loss to inch down rather than fall quickly. The tiny step size makes each update conservative, useful when curvature is unknown or noisy, but costly for time. Mapping this to practice, small learning rates are safe during early debugging and for very noisy gradients. But they will need more iterations on real datasets and larger models. Next, we will compare multiple learning rates and pick the best by final loss. This snippet compares learning rates and selects the best by loss. This code runs short training runs for a list of candidate rates and records the final loss for each. It then selects the rate with the lowest final loss as the winner. The important parts are the sweep over rates, identical initialization for fairness, and the metric used to compare runs. By keeping runs short, you get fast feedback about promising rates instead of waiting for full convergence. In practice, this is a simple hyperparameter search step you can run or a small validation set. Changing the grid of rates alters how coarse or fine your search will be and affects computation time. Next, we will show what a too large rate looks like and how decay can rescue training. This snippet shows a too large rate diverging and decay rescuing it. The example runs gradient descent with an intentionally large rate and demonstrates that the loss increases or oscillates, indicating divergence. Then it reruns with a simple decay schedule that lowers the rate over iterations and shows the loss stabilizing and falling. The key lines set the large initial rate, apply updates that overshoot, and then apply a multiplicative or step decay to the rate. This highlights two lessons. A large starting rate often breaks training, and a decaying rate can tame exploration into a controlled descent. In real training, decay can convert an aggressive start into stable convergence. Finally, we will try a one-step look-ahead to choose a rate automatically and train cleanly. This snippet picks a good rate by one-step look-ahead and trains cleanly. The code tries a small set of candidate rates and simulates a single gradient update for each, evaluating the immediate change in loss. It chooses the rate that gives the largest immediate loss decrease without increasing loss, then proceeds to run a full training loop with that rate. The crucial idea is cheap foresight. One simulated step reveals whether a rate will improve or break the loss. This balances safety and speed, and it often finds a solid starting rate with minimal extra work. In production, you can extend this to batched look-ahead or periodic rechecks to adapt as training progresses. Quick recap. What it is: a tiny experiment that shows 3 regimes of learning rates. When to use it: when your loss is flat, slow, or exploding, and you need a quick diagnosis. One caveat: toy convex behavior is simpler than real networks, so expect noise and curvature to change details. Next step: scale the same process to a small neural net and add periodic one-step look-ahead checks during training to adapt the rate as curvature changes. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.